So last time we were talking about statements versus predicates. Remember, a statement is a sentence that has a logical truth value. Meanwhile, a predicate is like a statement, except its truth value depends on a variable. Like here's a simple example. Say the predicate p of x could be that x cubed is equal to 2. Okay, clearly the truth value of this predicate depends on what x is. Like for example, if x is 0, then I get a statement p of 0, which is the statement that 0 cubed equals 2, which is clearly false. 0 cubed is 0. But if I plug in a different number, for example, the cube root of 2, that's the only solution to this equation here. If I plug in the cube root of 2, this is the statement that the cube root of 2 cubed, there we go, equals 2, and that's clearly true. So the truth value of this predicate here depends on what x is. What I want to talk about this time is how to use quantifiers to turn a predicate into a statement. That's what quantifiers do. They turn predicates into statements. And there's two quantifiers that we use. The first one is called the existential quantifier. And the notation for that is we write, for existential, we use this backwards e, and we say there exists a real number x such that p of x. Okay, so if you write that out in English, you read it as there exists. So that backwards e stands for exists. Some real number x such that p of x. And p of x is the statement that x cubed equals 2. Okay? Another way to read it would be, say, x cubed equals 2 for some real number x. And maybe an even more different way to read it would be x cubed equals 2 has a solution, x a real number. Okay, there's multiple ways to read this sentence out. But the most important thing is that for this existential statement to be true, it only needs to be true for one value. So the fact that it's false for 0 doesn't really affect the truth value of the statement. The fact that it's true when x is the cube root of 2 makes this existential statement true. So this statement is true because p of x is true for at least one value of x. P of x is true for at least one value of x. Namely, x as the cube root of 2. Okay, so that's the existential quantifier. For the existential quantifier to be true, the statement only needs to be true for one value of x. To contrast that, we have something called the universal quantifier, the other way to quantify a predicate. And for that, we write an upside down a. An upside down a, x a real number, such that p of x. Okay, and that upside down a stands for all. So this statement is read as for all x, real number, p of x is true, so x cubed is 2. Or you could say x cubed equals 2 for every real number x. Okay, multiple ways to read this sentence. For all is okay, and so is for every. Now clearly, it's not true that x cubed equals 2 for every real number. For example, if x is 0, then x cubed is not equal to 2. So here's an example where a universal statement is false. And the reason this is false is because p of x is false for at least one value, for some x, real number. Namely, in this case, you could pick really any number of values. Let's just say 0. You only have to give one example to show that the statement's false. Okay? So that's the two ways that you can quantify a predicate, the existential quantifier and the universal quantifier. Now, one thing I want to point out is that it actually matters if I say that I'm quantifying over the real numbers. If I quantify over the integers, for example, so this is just a little warning, if I said something like there exists an integer x such that x squared or x cubed equals 2, which one was it? X cubed, right? X cubed equals 2. Well, then this statement's actually false. There's a real number satisfying this equation, but there's no integer satisfying this equation, right? So it actually matters. The reason this statement is false is it actually matters what set you quantify over. Some sets the predicate might become true. Some sets the predicate might become false. Okay, so all these are examples of quantifying a predicate with a single variable, p of x. Now, if I had a predicate with two variables, things get a lot more messy. So let me give you an example of that. A simple example of a predicate with two variables. Let's say Q has two variables s of t, or s and t. And Q of st can be the statement that, let's make it simple, that s is less than t. Okay, so as an example, Q of 0, 1 is true because 0 is less than 1. But Q of 3, 2 is a statement that 3 is less than 2, and that's false. 3 is not less than 2. Okay, so let's quantify this predicate. And since there are two variables, we have two variables to quantify. So we can use two quantifiers. So a very simple way to quantify is let's quantify s universally, and let's quantify t existentially. So for all real numbers s, there exists a real number t such that s is less than t. Okay, so now I've turned this predicate into a statement by quantifying the variables. So now, is this statement true or false? Well, you have to try to read it in English, try to interpret it into normal English. This statement is saying, no matter what real number s I start with, there's always a real number t that's bigger than s, right? So I can say, you could write this as any real number has a real number above it. Any real number s has a real number t above it. And that's definitely true. Like, if s was 3, then you could take t to be 5. Or if s was 100, then you could take t to be 101. You can always just add 1, for example. No matter what s is, you can always take t to be s plus 1. So this statement's actually true. Okay? Let's quantify it a different way. Actually, let's take the same thing almost, except let's just rearrange the quantifiers. Let's quantify t first. Say there exists a t such that for all s, s is less than t. Now you look at this statement and say, okay, is that true or false? Let's try writing it in English again. Let's say this says that there is a real number, t, such that every other real number is below it. So this is kind of like saying there is a real number t bigger than every other real number, or bigger than all real numbers. Okay, and obviously that's nonsense. There's no way that there's one number that's bigger than all of them. There's infinitely many real numbers, and none of them is the biggest one. So this statement's actually false. So what I want to point out here is that if I quantify the same variables except in a different order, that can completely change the meaning of a statement. It can turn from a true statement to a false statement. This first statement is completely reasonable, and it's true. But this latter statement is not just false, it's very, very false. There's no way it makes any sense at all. So order of quantifiers is really, really important. order of quantifiers can really change the meaning of a statement. Okay, a lot of people accidentally switch order of quantifiers, and that's a big no-no. Okay, let's give some other examples of quantifying this statement. Let's say there exists a real number s such that, or maybe let's just say there exists a real number s, and let's use existential quantifier for both s and t. So there exists a real number s, and there exists a real number t such that s is less than t. Okay, well, remember, there exists means that you only have to exhibit one pair of real numbers, or one real number s and one real number t, satisfying this property. So can you find real numbers s and t satisfying this property? Sure. I could take s to be 5 and t to be 71, for example. That's not the only pair, but remember, existential quantifier means I only have to find one. There exists at least one pair. So this statement's true, and you could say because it's true, for example, for s equals 5 and t equals anything really, 73, anything bigger than 5. Okay, so it actually really matters what quantifiers you use. And another thing is, let's see what happens if I change the real numbers here to some other set. Let's say the positive integers. There exists, let's say, a real number s such that for all natural numbers t, or maybe let's call it n, all natural numbers n, s is less than n, or which is q of Sn. And it doesn't matter if I call it t or if I call it n, as long as it's clear what the meaning of the statement is. Right, this thing here is the same as q of Sn, the statement that s is less than n. Okay, now is this true or false? Remember when I quantified earlier something similar, there exists t such that for all s, it was actually, I ended up with a false statement. But this time I've got a true statement, right? Every natural number, for example, is bigger than 0 because the smallest natural number is 1. So in this case, the statement ends up being true. So again, you're seeing that it actually matters that I quantify over the real numbers or the positive integers or the rational numbers. It can change the meaning of the statement. Okay, so here's an example of quantifying a predicate by using two quantifiers. Okay, and now another really nice thing with quantifiers is now that we have all these symbols, it's nice to be able to do this process of converting between symbols and plain English. So let's do some practice with that. I made some little exercise here for us to practice converting English sentences into symbols. So here's one. The square of any natural number is positive. So the key word here is any, which is cluing you in that you should be using a universal quantifier. So the square of any natural number is positive. So I say that for any natural number, when I take the square of n, I get something positive. Okay, so that's how you convert this English sentence to a logical statement involving symbols. Okay, that's how you use logic symbols to form an English sentence. Now, how about the second one? Every non-zero rational number has a reciprocal. Okay, and again, it's saying every. So I know I'm supposed to be using the universal quantifier there. But then it also uses the word has a, meaning there exists a reciprocal for every non-zero rational number. Like every non-zero number has its own reciprocal. And that's cluing me in here that I should be using the existential quantifier. So every is for all, and has a is usually something like there exists. So one way I can write it is every non-zero rational number, let's call it x, every non-zero rational number, and to specify that x is non-zero, I could say q, and then take the set theoretic difference and remove 0. So q remove 0 just states that x is non-zero. Okay, for any non-zero rational number, a reciprocal would have to satisfy something like x times y equals 1. So I have to say every rational number has a reciprocal. So every rational number has another rational number y such that x times y equals 1. Okay, remember this is the multiplicative inverses axiom for fields. Okay, and here's one more. For all, okay, well it says for every, which tells me that I need to be using for all there. Every non-empty set of natural numbers has a least element. So there it is again, has. So I'm clued in that I should be using there exists. Every non-empty set of natural numbers. Okay, so maybe I should write it as for all sets of natural numbers, so that means S is a subset of n of the positive integers, there exists a least element. Now what does that mean? What does least element mean? It means some element of S, some, let's say, element, let's call it n in S, which is bigger. When you say least, it just means bigger than everything else. Oh, sorry, no, it doesn't mean bigger. It means smaller than everything else. Least means smaller. It's the smallest possible one. So some n in S, which is smaller than every other m in S, which means that n is less than or equal to m. Okay? And now that's kind of weird, right? Because now I have to quantify, well, I use the word every again here. So that's indicating to me that I should be using a for all quantifier. So I have a for all quantifier here, a there exists quantifier here, and another for all, or universal quantifier. Okay, so I say for every non-empty set of natural numbers, so I have to specify that S is non-empty. There exists a least element. So there exists some element n in S such that n is bigger than, or sorry, n is less than or equal to every other m, such that for all other elements of S, n is less than or equal to m. So see, you have to be able to tell when you need a universal quantifier. Like in the original reading of the sentence, it just says every non-empty set of natural numbers has, so I have two quantifiers, but then you have to kind of interpret the word least and realize that that word itself has baked into it another quantifier, another universal quantifier. So to write this English sentence in symbols, I need 1, 2, 3 quantifiers. Okay, and then there's also subtleties, small subtleties, like don't forget to mention that S is non-empty. Things like that. Now, you might be wondering what these brackets are for. That's just for readability. Like if I didn't have those brackets there, already the statement's somewhat difficult to read. If I remove the brackets, then it's just even more difficult to read. That's all the brackets are for. Okay, so that's how to quantify, how to write a plain English sentence using logical symbols. And I have a couple more exercises for you over here, just to check if you're understanding what I'm saying. So here's a couple sentences written with logical symbols with quantifiers, and I want you to figure out if those are true or false. And you can put your answer in the comment down below. And here's a couple exercises where I ask you to convert between symbols and plain English. So here are a couple plain English sentences that I'd like you to convert to quantified logical statements. And conversely, here's a symbolic statement that I want you to convert into a plain English statement without using too many symbols in it. So this third exercise here is actually pretty tricky, so I'm really curious